Hi everyone, I hope I'm audible. Welcome to the free session of parametrized. We'll be dealing with parametric architecture and looking into what exactly parametric architecture is and what computational design is. More on that in a bit. Let's give it a couple of minutes so that our audience can settle down. People are still joining in and leaving, so it is also being live streamed on YouTube, so if someone in the chat box can let me know that if the stream is running fine and if you can hear me properly. Can you guys hear me? Great. Thanks a lot. Thanks a lot. Okay. So, before we begin, I would like to know first what is your level of understanding when it comes to parametric architecture and computation design? What would you rate yourself? Are you a beginner or you have some sort of intermediate experience, or if you have been using the tools for quite a long time now, so you must be at an advanced stage. So how about typing that in the chat box so that I can know what sort of audience do we have today and I can tweak the entire presentation and the things that we're going to go through accordingly. So zero experience. Okay, great. So maybe write down beginner, intermediate, or advanced in the chat box, and people what connected with us on YouTube, go ahead and let us know your level of expertise in the particular field. Okay, so I see a lot of beginners here. That's all right. Okay, so I see that it's about the ratio is about 60-40, 70-30, something like that. So I'll try to keep it as basic as possible, and I try to break things down in a way that you guys can understand. So let's begin. I'm architect Chinmay Gaur, a co-founder of Equim, and Equim is an architectural and research organization, and we, along with doing architectural projects, both trying to fuse vernacular architecture with parametric architecture and finding out the new ways how we can innovate in this particular field. We are also into education and research, where we believe that architecture is a profession where collaboration is very important among people, among students, and among professionals. So that is what we look forward to, and we train students and architects in the field of parametric architecture and computation design because we understand that it's a necessity now, and we are living in a digitalized era, and we have to take steps forward and we have to see how we as designers can innovate ourselves and our design process so as to meet the 21st century advancements. Okay, so let's begin with the presentation. So let me walk you through the things that we would be covering today. So first of all, we begin by understanding what exactly parametric architecture is. What is the effect of parametric architecture in the whole practice, both on a global scale and on in a localized manner, how parametric architecture and this machine learning artificial intelligence is kind of gradually taking over. And also after that we'd be looking into Rhino and Grasshopper. So I'll try out with you guys today. I'll try out some very basic exercises so that you guys can get started, get an idea of what exactly it is and if it is something for you or not. And then finally we would be looking into some um, relevant things through which you can actually bring your designs to the real world. Yeah. Okay. So also, before beginning, I would like to ask all of you to leave your registered name, the name through which you registered on the website, and your email ID in the chat box. People on YouTube go do that so that we can share some of the resources with you. We want to share some files. We want to share some study material with you so that you guys can get a head start. So leave your email ID and full name in the chat box, and I believe the team meanwhile is also taking care of the chat box. So if you have any questions during the presentation, you can drop them in the chat box as well. All right. So let's begin. Okay. So Andrew McAfee, founder of McAfee antivirus, and he is one of a very renowned data scientist, said that the world is one big data problem. So, what exactly did he mean by saying word is one big data problem, and why it is relevant to us as architects? So, if you actually dive into it, if you actually think about it, you'll realize that data has been there for centuries. So the scientists who are working in NASA or SpaceX or in any other field, in biology, in chemistry, in the physical world, uh, you have to understand that scientists are discovering that data. It is already there. There are mathematical relations among the constellations and among the stars, among the patterns that you see in the leaf or on the drought land, and pretty much everything that has been created organically. Uh, there is a certain mathematical algorithm behind it, and if you dive deeper into it, you can break that down. So, similarly, everything around us is actually one big data problem, and it is the intent of the human nature to actually accumulate that data, spot patterns, connect the dots, and find something meaningful out of it. So, and let's take a moment to think that while we are living in a century, while we are living in an age where we spend about uh, let's say about 30%, 35%, and in some cases about 55 to 60% of our time on mobile phones or on laptops or computers, we are living in a very digitalized world right now. But if I take a moment and if I say that that particular digitalization also reflects in our society, in the buildings that we create, in the construction industry, in the architecture, the road networks that have been designed in a way that they never lead to traffic jams. The infrastructure is just great where it can adapt with the humans and change, and it is very sustainable, and we are doing great things in terms of architecture. So I would be lying, right? The thing is, we are very far away from digitalized architecture. We are very far away from the point where we can say that our road networks don't lead to a traffic jam. We are very far away from saying that the buildings that we are constructing every day, they are sustainable. They are 100% sustainable, or they are very, very much energy efficient and things on those terms. But right now, we are very far away from all of that. And we as architects are to blame as well. Let's see how. So before we dive into understanding what parametric architecture is, it is very essential to understand what parametric architecture is not. So I'm sure you must have seen these buildings all over on the social media, or while you must be researching or trying to take some inspiration from some of your projects. So the first building in Azerbaijan by Zahadi, the architects, and Guggenheim Museum, these buildings go synonymous with parametric architecture. You hear the word parametric architecture, and the images of this building pops in our head. But let me break it down for you. If a building looks complex, if a building looks organic, twisted, very curvy, it does not necessarily mean that it has been designed parametrically. You can pretty much design a cuboid and it could still be parametric architecture. So parametric architecture is much more than that, much more than just the form, much more than what you're designing. It is actually about optimization that we are going to learn in a bit. And also people think that uh, when you're designing something parametrically, the software does all the work. You just have to tell it something and it will give you all the design solutions on its own. So that is not true. Let me break that bubble here. That is not true. So when you're working with the softwares, it's a tedious job, and you have to work with it constantly. You have to kind of, okay, am I muted? Can someone tell me in the chat box? Okay, I guess it was some network issue. All right. Okay, great. So Software will not give you the designs ever. You have to work with it a lot. It's a lot of to and fro process in which you start working on something, then software takes it forward, then you take it forward, and then you realize, okay, there is something missing, there is some error. You have to circle back to the scratch, you have to start again from the scratch. So it's a very lengthy process, and um, but definitely a fun process as well, because it makes the design um definitely more efficient in terms of what we would be able to design manually if it had to be designed manually entirely. So before we move forward and get a glimpse of the tools of future, or let's say not so far of a future, there are in the present world and we are using them constantly. But before talking about the present and the future, let's try to understand the past a bit and see where we evolved from and how did we reach to parametric architecture. So humans or Homo sapiens, we evolved from here. We were early cavemen who fought for shelter, who wanted shelter and food to survive, and that was the basic motto. And look at where we are right now. I'm sitting here in India and I'm communicating with all of you sitting in different continents in different time zones, and this is where we have reached. But this is how we have evolved. We are almost a cyborg, and we'll see how. Let's also talk about evolution of automobiles for a moment and see how other fields are evolving in when it is being compared to architecture, and how architecture evolved and how other fields have evolved. Is there a difference in the evolution? Is the graph same of all the fields, or is architecture lagging behind somewhere? So that is what we have to understand, and see if there is a gap and how can we exactly bridge it. So this was a stone wheel uh, that was made by early human beings, and it was tied to a cart, and humans started pulling it. It became a pulling cart, and then soon animals were tied to it, various different animals. It became a bullock cart, and then soon a motor engine was developed. And after a motor engine was incorporated with these wheels, sorry, with these, yep, with these wheels that were no more of stone but were of rubber, it became a modern day car, the car that we drive on a daily basis. But did we stop there? Once we had the car, did we stop there? No. You see companies like Tesla and Porsche and Ferrari, they have been constantly innovating. BMW and Mercedes, they have been constantly innovating and trying to incorporate AI in the vehicle. And it is no more a fiction, it is reality, where the automobile itself has a brain on its own, where it can communicate with the vehicles around it, where it can communicate with the obstacles, it can understand the user, and based on that, make decisions on its own. So, in a sense, can we call it a non-living thing anymore? No. It has become kind of a synthetic living being, if you will. So that is how automobile industry has evolved, where the vehicles have a life of their own. Let's talk about computers, how computers have evolved. So most of you must have read about abacus, that was invented by Charles Babbage. So back then they moved these beads up and down to perform basic mathematical calculations like addition and subtraction, and it was very slow. It was a lot of physical work and it was very, very slow. Now we have reached to a phase where we have quantum computers and we have supercomputers that can perform tasks, that can do calculations unfathomable to the human brain. We cannot imagine the level of complexity that the calculations these machines perform on the right, and that too in matter of seconds. So that is how computers have evolved. That is how the processing power has evolved. And definitely, as we all are architects or related to architectural field, we have to talk about evolution of construction. I would also like to know how many of you are architects in or future architects in the audience today. So guys on YouTube and on Google Meet, drop down whether you are an architect or architectural student, or if you are from some other field, drop that down so that We know the sort of audience that we have today, the bunch of audience that we have. Okay, so construction industry evolved from chiseling the stones to mere find shelter, and gradually, I don't want to get into the history of architecture and history of construction because I'm sure most of you must have already studied that somewhere at some point or the other. So we started off by chiseling stones, and then we moved to stone masonry and brick masonry, mud mortar, cement mortar, concrete, tensile structures, and trabeated structures and prefabricated systems. And now we have reached a phase where we are standing in the age of 3D printing, where drawings are directly exported from the computer, imported into the machine, and they are directly 3D printed. So the image that you see on the right here, it's a robotic arm that is directly printing concrete in the form of these vases. And constantly the researches are going on of how we can scale this process. So it is and we have had a lot of researches, and recently government of India signed up a contract with L&T, Larson's and Turbo, where they would be 3D printing houses of 1000 square feet of 2 floors, um, about 900 to 1000 units of them. So it's no more a thing of future. We are in that phase, and gradually down the line, probably 2 years from now, 5 years from now, or 10 years from now, entire houses would be 3D printed, and somewhere down the line, even the cities would be 3D printed. So that is what we have to look forward to, and that is what we as architects have to evolve and understand, that if we have to cope up with the technology, because construction industry is going to evolve up to that phase, because that is economical, you do not need a lot of human intervention when machines are working. So construction industry will definitely go there. So it is up to us whether we want to be there, we want to be the ones who design it, or should construction industry take over the designing process as well. And if I talk to you about evolution of technology, so this is a Moore's law graph, and I would not get into the technicalities of it. I just want to give you an idea of the pace of which technology is evolving, or the processing power is evolving. So what this graph basically means is, let's say if I have a computer chip, the green sort of chips that you see inside the computer. So if I have a chip, and if the size of this chip is 1 square nanomillimeter, 1 nanomillimeter square. And if I can fit 10 transistors, transistors are the units that are responsible for processing. So i5 has more number of transistors than i3 computers, or i9 has more number of transistors than i5. And similarly, in the phones, the upgraded phones or the updated phones that come out every year, they have more number of transistors in them. So if in year, let's say 2020, we can fit in 10 transistors in 1 nanomillimeter square of an area of a chip. So by the year 2022, the sizes of transistors would go down, and we would be able to fit 20 transistors in the same area. So what that basically means is, computation power of machine of mobiles or computers doubles every 2 year. So to put it in basic terms, or in a way that you guys can make sense out of it, is would be, imagine how many apps and softwares are pushed out on a daily basis in the market. By the time I would finish this webinar today, there would be some new apps pushed out in the market to be tested. So that is the pace of technology, that is how the technology is evolving. So we have to keep up with that as well. Okay. So let's also talk about evolution of classrooms while we are at it, because you see there is some sort of lag, because industries have been evolving quite quickly, technology is evolving quite quickly, but somehow the designers are not. Uh, I mean, if there are 100 designers, probably 10 of them do some extraordinary work, 90 of them are either in mediocre or below mediocre range. So why is that? Why are we still in a place where we are not able to bridge the gap? Let's talk about evolution of classrooms. So this is a classroom from 19th century where there is a teacher standing in front and there are some students listening to him, right? And there's a blackboard on which he draw and explain things. And I want you guys to take a moment out here and think about the classrooms you sit in today. Or if you are professionals, the classrooms that you used to go to when you were a student. Take a moment here and try to think about it. This is how what a modern day classroom looks like. So instead of the teacher drawing on the whiteboard entirely, he also has a projector that would project some images on the screen here, right? And students would carry their mobile phones and laptops. That is the only thing that has changed. The way we gave education has not evolved at all. How comfortable the students are feeling while architecture itself is science and art combined. So art cannot be taught formally like science is. So there has to be some sort of informalness to it through which you feel comfortable, you can express your thoughts, you can express your emotions and then study, right? So there is a definite need of evolving the classrooms as well. Now let's talk about evolution of architecture because that is why we all are here, right? So let's talk about evolution of architecture. And before we do that, someone from the team would be dropping a link to the WhatsApp group. So you guys can join in the WhatsApp group that we have created in which we keep on sharing some educational resources and stuff. So and about some events that we do. So if you're interested, you can use the link in the chat box to join the WhatsApp group. Okay, moving forward. I again do not want to get into the history of architecture here, but we basically started off where we use these stone slabs to make a very basic shelter in which early humans would sit to find shelter from harsh weather conditions or animals. And then they gradually started building up walls because they needed some privacy. And thus came a house. And then they wanted to live in neighborhoods, so they started building societies. And then the area wasn't enough, so they started building on in levels. So stories started rising, stories or number of floors started rising, and then we moved on to so many types of architectural styles. And if you move from one city to the other city, you'll notice the change in architectural style. So architecture has evolved quite a lot. It has evolved to a point where we have built things, we have built sort of the buildings that people would not believe 200 years ago. If you told someone from 200 years ago about Burj Khalifa, they would not believe it. So now we have buildings that are 150, 200 stories high. So that is where we have reached. But is that enough? Or is that actually on the par with all the other fields that have evolved? Let's check that out. So let's also talk about evolution of architects while we are at it. So on the left, what you see is an image of architects probably 150 years ago when there were no computers. So imagine if someone had to make uh, Burj Khalifa back then, how would they do it? Or so they would basically lay down huge sheets of paper on the ground, and 15 of the draftsmen and architects would climb onto it and start sketching things out, and that's how they would evolve the designs. It was a very lengthy process, very tedious process, took a lot of time, took a lot of effort, there was a lot of reworking. Now that has been fixed by the image that you see on the right, thanks to the CAD systems that we have, thanks to the CAD and BIM tools that we have now. So we are at a level where scale is no more an issue, right? You sitting in front of a screen, you can design uh, a space as small as a room, a small bedroom, or you could design Eiffel Tower on it. You could zoom in as much as you want and you could zoom out as much as you want. Scale is no more an issue. One single person sitting in front of a screen with a computer can do that. But the thing is, earlier when we had to draw a line, We took a ruler and we took a pen, and we drew a line manually. Now we have to when we have to draw a line, we give a command called L enter on AutoCAD. If you guys use AutoCAD or any other similar tool, you must know. So the manual work is still there. And who is the person who is the one who's making all the decisions? Is it the computer or is it the human? The human, right? Where we definitely know that at some point, at certain stages, computers can make better decisions than humans. So we should definitely employ them at those places at least, right? And there is a reason why architects have not evolved. If we actually talk about other industries like healthcare, or let's say IT. So healthcare has robotics built into it, where robots are doing surgeries and all of that stuff, because they have this proper research institute set up that only work for technological development of healthcare infrastructure, right? But not a similar faculties available for architects. So that is a reason why architects have not evolved, and definitely we are lagging behind. So let's have a look. So the biggest reason that was found is we are a bit slow to adapt to the technology. So you would find it hard to believe when CAD systems became popular, or when they were just becoming popular, architects did not want to move from manual drafting to CAD systems or to computers, because then they would have to train all of their resources, train themselves, spend time, change the entire workflow of how the office functions, and then move to the new software or new tool and then start working on it. But when they realized that the market was taking over, people who were using CAD systems were taking over, that's when they evolved. So that is what a challenge here is as well, because the larger firms that are out there are not willing to evolve. But now a trend shift or a paradigm shift is happening, where more and more young professionals are interested in this field and they want to do something different, something new. Um, and definitely parametric architecture is like the design style of 21st century. So students want to keep up with that, and that's why there is a definite need of this whole workflow change, and that is what we are trying to accomplish here. So let's move forward, and let's understand why it is necessary to evolve right now, to make sure that we as architects are evolving right now. So built environment is for the people. Hence, it must progress in step with the progress of society. What I mean by saying this is, imagine if you had to. I don't know how many of you have read about Indus Valley civilization, or you must have definitely read about the pyramids. So, how do we know that those people were, when it came to construction, those people were very evolved, those people were very smart? How do we know that? By analyzing the sort of structures they built. Now imagine if a meteor crashes on Earth and all the life form as we know it extinguishes, ceases to exist, and if aliens come on Earth and they want to understand what sort of technology did the people here have, so would they be able to guess that? So if they came to your house, would they know that the smartphones that you were using had AI enabled in it, had machine learning incorporated in it? No, because our buildings, the buildings that we live in, do not reflect that. And merely putting 10 different sensors to control the to control water sprinklers, to automate the door openings, was a smart thing to do like 10 years ago. But it is a dumb thing to do right now and call it a smart building. The definition of smart building has changed. You see the definition of smartphones change every year. Right. So similarly, the definition of smart buildings have changed, and our built structures should reflect that. The technological advancements of the society should be reflected in the built mass as well. And this is what humans of this is what is the plan for the future humans. So Elon Musk, there's a company by Elon Musk, it's called Neuralink. So if someone of you have read about it, you must already know or that Neuralink has already started testing these chips that would be implanted in the heads of humans, and they have started off with animal testing, and gradually it would be just a matter of time when all of us would be wearing weird hats that had chips planted all over inside it, and we would be connected with internet. Because you see, the problem currently is not with the computers, it is with the humans. So try to think of the internet speed that you are currently having. Probably it is in gigabits per second or megabits per second, right? So computers can communicate with each other at a very fast speed. You can take the input from the computer at a very fast speed because you can listen, you can see the things on the computer. So the input rate of humans is very high. But when it comes to giving the output, how do we give the output? Using these 10 fingers? Or when we talk about the phones, we use these two thumbs. So the output rate is less. But as soon as a chip is implanted in the head, that would be fixed. And there would be a very big, exchange of data that would happen, and that too at a rapid rate. So we have to prepare for that as well. So this is what the future of humans would be: full symbiosis with artificial intelligence. I mean, at least that is predicted. So let's see how we can evolve our buildings on a similar terms. So when we talk about computation design or parametricism in itself, the most important thing is data, and how do we interpret that data. So if I give you an idea, one zettabyte is 1 billion terabyte, and in the year 2010 we produced about 4 zettabytes of data, not even 4, about 3 zettabytes of data annually. And by the year 2020 we produced somewhere around 52 zettabytes of data. And but it is predicted by the year 2025 you'd be producing about 175 zettabytes of data. So every click that you make on the internet or on your phone, or every selfie that you click, that you upload, uh, amounts to the data, right? So that is a huge amount of data that we are producing, that mankind is producing annually. And corporations like Google and Facebook, they have the capacity to take down entire governments. So that is what we are dealing with. And while I'm talking about data, it is necessary to talk about the architectural data. Now let's bring in the architecture into this whole thing, and let's redirect this conversation focused towards architecture and parametric architecture itself. So whenever we are presented with any design challenge. So, guys, if you have any questions during the presentation, or during I'm going through when I'm going through the Rhino and Grasshopper hands-on, if you have any questions, you can post them in the chat box, and here and there, I'll try to address them all. All right? Okay. So, whenever we are presented with a design challenge, be it a hypothetical exercise or a real live project design challenge or a problem, right? I could also say a design problem. What do? We collect data, right? Data like what is the bearing capacity of the soil of the site? What are the visibility angles? Where is north? What is the wind condition on the site? What is the rain condition on the site? What is the humidity level? What sort of what is the sun movement? And what sort of buildings surround the site, right? And seismic data, what sort of earthquake zone does it fall in? And you know what is the how deep is the groundwater that is available. So all of those things we try to analyze, we try to collect the data of it. And if I tell you that all of that data is very scientific in nature, so this data that we collect is scientific in nature. So if I ask you, what does the unit, what exactly does the unit of precipitation mean, or what are the azimuthal numbers of the sun? So we would fail at that because we are architects, right? We are not geologists. We have not been trained to read that data and understand it perfectly. We are just trained to read that data and make some sense out of it, so that when we are designing, we can, reflect some of that in our designs. But that is a very fairly scientific data that should be given due consideration, considering the sort of world we are living in that is gradually heading towards disintegration. And after we have completed the concept, after collecting all this data, what do? We make a design concept and we produce a design. And after we have produced a design, then we worry about things like the materials that we are going to use. How much material, how much heat would that material absorb, or how much would it give out? Or the openings that we have designed in the building, how much air would the building take in, how much would it expel out, and all of that stuff. Again, that would be very, the solar radiation, the shadow analysis, all of that is again very technical in its own terms. So just to help you understand better, I'll just name it as tangible data, and you'll understand why I'm saying this. This all tangible data is very scientific in nature, right? Okay, so I'll circle back to this tangible data. Let's talk about digital in architecture and see how we can use that data digitally in architecture. So if I talk about evolution of manufacturing, I'll probably go through a couple of slides quickly. So this was during and before Fordism. So this is a construction line or manufacturing line in which, this person might be associated to place the wheel in place. This person might be there to just place the bolts or the screws on it. And this person will be there to just fasten those bolts on this wheel. So every person has its own defined job, and it is just sheer manual labor. There is no decision, there is no basically uh, conscious decision that is being made, right? So post Fordism, all of this was automated. We had robotic arms. We have robotic arms that do the same thing. One of the arms would place the wheel, other arm would actually place the bolts and screws and nuts, and the other one would actually fasten them. So this change, you see, for you can see the difference. Humans have been replaced by machines, and these humans have been put to better work because we can think and we can innovate. So why waste time on sheer labor where there is nothing new to do, right? And if I talk about building construction, this is what a usual construction site looks like, right? And I'm not talking about a very big, extremely big scale construction. Uh, a small to average range construction looks something like this. And there is no automation. There are some JCBs, there are some machineries that would mix up the concrete and pour the concrete and vibrate the concrete and all of that stuff. But there is not a lot of automation in it. So this is something that we have to understand, and we have to bridge this gap as well. How we can automate this construction part as well, right? So, so now let's talk about parametric architecture in detail. So parametric architecture, when it popped up, it popped up somewhere in early 90s. So there were like two, three stages of parametric architecture. And the very first stage was folding in architecture. So folding in architecture became popular with the introduction of tools like Maya. So I don't remember the exact name with which Maya was initially launched in somewhere in between 1994 1995. It had a different name, and then gradually they changed it to Maya. So, what Maya offers is a great capability to edit the buildings. So, folding in architecture meant one single surface, one single continuous surface that is morphed in a way that it forms ceiling, it forms floors, it forms walls, and everything is one seamless single surface. And as you can see here, it is one single seamless surface. But there was sort of a toll of this sort of architecture, and the toll was every piece that you see here had to be custom made for this particular building, had to be custom made. So things that are mass produced like this is mass produced, right? So things that are mass produced like this could not be used here, and the cost of the project was very high, and the time it took was very high, and the precision that it took was very high as well during construction. So this was, I mean, to some extent it was a success. It was a different type of expression in architecture, but overall it was kind of a drawback and a kind of a waste of resources. So then came in the next stage in parametric architecture, or let's say, yeah, exactly, parametricism, with the introduction of tools like Grasshopper. Now, Grasshopper is a visual scripting tool, and we'll be trying our hands on today on a couple of exercises in Grasshopper and Rhino right after this presentation. So, stay here. So, those of you who are joining in now on YouTube or on Google Meet, if you haven't left your email IDs and your name on the chat box, do that right now. We want to share some resources with you. So, once you do that, we'll be sharing some resources through email with you. All right. And if you guys are interested in joining a WhatsApp group where we keep on posting educational stuff related to parametric architecture, you can definitely check out the link that is posted in the chat box. Okay. So Grasshopper is a visual scripting tool. And what does it do? So it has a very tight integration with Rhino, and Rhino itself is like a 3D modeling tool, just like SketchUp or Maya or 3ds Max, any other 3D modeling tool. Rhino is a bit sophisticated and is dependent on a lot of mathematical calculations. So Grasshopper starts from Rhino itself, and there are these components. So these are basically component palettes that we'll explore in a bit, and these are components, and we connect these wires here and there to, define some sort of logic in these components, and the all of these components have a pre-written code inside it. Pre-written code inside it. So, and they are set to do certain tasks that we'll explore gradually. So, and this is a canvas on which we place everything. And the parametric architecture changed forever, for real, with introduction of Grasshopper. So now comes in the stage, the latest stage of parametricism, that is Tectonism. Now, Tectonism is a very beautiful or very, technologically advanced stage of parametricism, in which you also write at the concept. Usually what happens is you have a concept, you make a design, you make working drawings out of it, or technical drawings out of it, or shop drawings out of it, and then while you're making these shop drawings, you think of engineering logics. Right. So at this stage, you think of engineering logics of what sort of material would be used, how the material would get joined with each other, what would be the structural elements, what would be, the curtain walls, and things like that. You take care of it usually in at this stage. But this changes with Tectonism. What happens in Tectonism is when you are at the conceptual stage, right at the conceptual stage itself, you understand what sort of material is mass produced and available in the market, what are the sizes of the uh, of the gypsum board, what are the sizes of the partition walls or the metal studs and all of that things, all of those engineering things, and you build it right here itself, plus engineering logics. You combine both of these and then come up with a design. So the designs that you come up with are already optimized in terms of engineering logics, right? So have a look at this image. So the structural elements that are here through which all these pieces of gypsum are joined in together or are kept in place are you were built in right at the inception stage of the project, and they do not work, they are not no more hidden, that work as hidden structural member, rather they have become a part of the design. So that is what we have to learn, and that is how we can make the best use of the available resources, right? Okay, now going one more layer deeper into parametric architecture and trying to understand what exactly it is. So I've been saying the word parametric architecture a lot. So parametric architecture, if I had to break it down in a definition to you, parametric architecture is trying to find the simplest solution. Solution would be a design that you produce. So finding the simplest solution to the challenge or a problem, design challenge or a design problem, with objective evaluation. So this is a keyword here, with objective evaluation of different parameters like these. By objective evaluation of all this data, and then we come up with the most optimized result. So you have get a design problem, you objectively evaluate all this tangible data and come up with a design that and come up with the most optimized design. That is what parametric architecture is all about. And uh, computation is basically generating solutions after processing it using mathematical algorithms. So when you are using mathematical algorithms, you would be able to spot some patterns in it, and you can connect the dots, establish some relations, some rules, some ground rules, and some guiding factor for the design, and then you can evolve your designs. Okay, and you will understand that in just a bit. Yep. So this is what a traditional workflow looks like. Let's have a look at the traditional workflow and parametric workflow. How does that differ? So we get a design challenge. We collect all the data that we talked about. So I'll just write tangible data like wind, sun, seismic activity, groundwater availability, soil bearing capacity, and all of that stuff. And along with that, we also collect some intangible data. Intangible data would be narrative behind the design, the concept or the emotion behind the art, or the requirements of the clients, the feeling of the clients, the feeling of the architects, the story that the architect wants to convey through the design. So what we usually do is we take this intangible data and tangible data, and we as architects we feed it in our head, and then we think of all of these things in our head itself. So based on our intuition, our experience, our subjectiveness towards the data, we come up with a result. Now the problem with the result is the solution that comes out is fragmented, or it is not absolute in nature. Why? Because we took all this scientific data that was there and we took it in our head, and we uh, thought of those that scientific data very unscientifically, using our intuition or using our subjectiveness. So that is why we can never be sure if the building is going to perform very nicely or very poorly until we build it, or else if we have to test it, we have to revert back to the parametric workflow. Now what is parametric workflow? You get a design challenge, you collect again the set of intangible data. So I would write ITD, intangible data, and tangible data, right? So what you do is you as architect take care of the intangible data, and you feed the tangible data to the computer or the computational tool, and combine both of them together to come up with a solution. If you are very happy with the solution, you can move forward with it, or if you're unhappy, you can always revert back, tweak your own inputs or tweak the this input and come up with a new solution altogether. Now the solution that you would be producing would be absolute in nature. They would be tested, they would be optimized, and basically there would be no loss of data. So let's say if the computer tells you that your building is 80% efficient in terms of solar gain or solar radiation, so now it is in your hand. Now it is on your conscious to either move forward with it or to do something about taking that 80% to 90% maybe. So now you wouldn't be making any guesswork, rather what you would be doing is your decisions would be informed. And this is the biggest thing that comes out of parametric architecture, that you will never make guesswork anymore. Everything, every decision that you would make would be informed. You would have logic or reasoning behind it. Okay, so I'll just quickly go through this slide. So this is traditional workflow solution. And I'm not saying that you only come across solutions like these when you're designing something traditionally. There have been great architects, and I'm you know, I really admire the works of some of the architects that existed in the past who have created some extraordinary designs. What I'm trying to say is when you move to tier 1 or tier 2 cities, you usually see buildings like these. Now, these buildings are very bad for Earth. Why? Because think of the sun. If it moves like this, all the faces that are there, all the niches that are created here, respond to the sun in a different manner. The wind energy that is there, the floors on the bottom level respond to wind in a different manner, the floors on the top respond in a different manner. And again, if you actually think about how it was designed, the usual workflow would be the designer probably designed one single floor and copied it in the height or in the z axis to come up with multiple floors, and then basically copied this tower multiple times in this group housing to come up with this entire array of these towers. Now the problem is this face here responds to the sun in a different fashion, and the rear face responds in a different fashion, and this one in a different fashion, and this one in a different fashion, and altogether this whole thing was never thought about while people were designing it. And again they had to make guesswork that okay, this particular block is falling in this direction, so it might be okay, right? So again there is a lot of guesswork. Let's see what parametric workflow solutions look like. So most of you must have seen Al Bahar Tower in Dubai, um, at least on the internet. So Al Bahar Tower, and there was a lot of optimization that went into Al Bahar Tower. I'll just cover one basic thing that they did. So they wanted to design a commercial place for commercial office space, uh, and they wanted to have glass all over it. But the problem with glass is the heat gain is very much. So they wanted to cut down that heat gain, so they wanted to design some sort of fenestration over it. So what they did is they designed this building parametrically, and they simulated sun and other sort of parameters that told them that this face here and the rear face will receive the maximum amount of radiation. So what they did is they designed a fenestration system for just this part, and it was a hexagonal ring that had flaps inside it that would open up when the sun is direct, when the sunlight is direct, and it would close when the sunlight is indirect to allow the indirect illumination to come in. And such structures that actually change their forms or move in real time to adapt to the human needs or certain environments are known as kinetic structures. So what I'm trying to explain here is maybe Al Bahar Tower is not perfect, but the first car that humans made, was that perfect, or the cars that Tesla is making today, are they perfect? No, but they are definitely one step further from what we had yesterday. So that is how we have to take these buildings, and we have to take inspiration from them, and we have to understand that we have to evolve these things further. This is like the first step. We have to take it to the second, third, fourth, and ultimate steps, and evolve it to a place where these solutions become permanent, and these become very sustainable. So that is what we have to look forward to, right? And this is a group housing by Zaha Hadid Architects, and you can see how this big high-rise tower is being received to the ground by these low-rise structures, and how if a wind would flow, it would automatically create tunneling inside it, and how sunlight would react with each of these faces. And let's say, for an example, I'm just giving an example here. So you see all these curvilinear buildings here. So just for an example, let's say that this face here, let's say this does not receive sunlight. When they designed it, the computer told them that this does not receive enough sunlight throughout the day. So what would the architect do? Either you can change the design, or you can plan certain activity that is not used during the day, right? It is active during the night, so you can fix the problem. Now you would be making informed decisions. It would no more be guesswork, right? So that is what we have to understand, that there is no time of guesswork now. And finally, let's also talk about why does architecture need computation design. So I'll just explain about the first couple of I mean, like the very nitty gritties of it. So there are a lot of things that parametric architecture or computation design covers, but the most important things that come out of it is, so we had to design we had to design a building in which we had to distribute the floor area ratio, or FAR, or the plot area, in the total built up that we could achieve. So what we did is we asked computer, or we made some algorithm, and we wanted to have some sort of courtyards and some level differences, so that there would be some tunneling effect, people could interact here and there, they could move. So uh, have a look what it did. So this is like the first iteration, in which the entire plot is being covered by, let's say, 4 floors. Then the computer drilled down one big courtyard, and now it has 8 floors. Then it made some smaller sized openings, and now it probably has about 9 floors. And then it started stacking, it started segmenting the floor slabs. And in the next iteration, we wanted to develop towers. So one half of the building is being occupied, one fourth is being occupied, and yep, one fourth is being occupied. And here 2 floors are covering the entire site, and remaining area is being covered by one fourth. And there is 1/2 distribution, and this is another 1/3, sorry, one fourth distribution, and then gradually getting else out of it, and then getting a different face. So, with what I mean by this is, if you make an algorithm, then you can come up with thousands of design. Computer, based on your algorithm, would generate thousands of design based on the complexity of your exercise, of how long the time it takes. But it would generate thousands of designs, and it would give you data out of it. Data like what is the area, what is the radiation, which is more sustainable in terms of wind and sun, and what is the wind movement, what is the visibility, all that data it would give with all the thousand results that it would give you. So then you can actually read the data and choose whichever works best for you, for the context. So that is how you can take it to the next level, right? And then there is something called repetitive task automation as well. So imagine if this was a building, the graphic or the geometry that you see on the screen here. So imagine if this was a building, and this building had these hexagonal openings, and it had about, let's say, 3,000 openings. And each of these hexagonal opening is of different size. So there is something called Door window schedule. Door window schedule. So what does door window schedule have? When you have to construct a building, you have to give it to the fabricator that has all the openings, all the doors and all the windows with their dimensions. So for this, it would have radius and what is the trim size of this guy and what sort of material is being used, what is the glass. So all the basically all the technical specifications of each of these windows, and you would have to make it 3000 times if there were 3000 different sized openings. So imagine how long would it take you to do on AutoCAD or any other CAD system? Probably a month or so. And if there is a slight change in the geometry of the building where the window sizes change, you would probably quit your job. You'd say, I don't want to do this, right? So with computation design, you could also automate this. So you can ask computer to start extracting all these windows, start making 2D drawings out of it, start writing down the dimensions and whatever specification it is that you need, and you can directly export a CAD drawing and send it to the fabricator right from the designing tool itself. So you can automate these tasks that do not require any design thinking, any critical thinking, but just require time and tedious labor. And then finally testing the design. So I cannot put more emphasis on this. You can test your designs. Let's say if you have, I'm trying to put it in as basic terms as possible. So let's say this is your tower. You can simulate earthquakes on it. You can simulate loads and see where exactly your structure is failing, or you can simulate the sun and you can simulate winds and see whether you have whatever you have designed is it working or not. So you can extensively test your designs out. So this is why architecture needs computation design. And that brings me to the end of the first presentation here. And I would love to hear some questions from you guys. And meanwhile, let me launch Rhino so that we can also try out a little hands-on on Rhino and Grasshopper so that we can get a little taste of it and see how things are when it comes to Rhino and Grasshopper, and whether it is very difficult to learn it, or is it just a hoax that people say that parametric architecture is way too complex to learn. Meanwhile, if there are any questions, please post them in the chat box. I'd be happy to answer them. So there is one question by Sabina. Does Rhino do all those stuff, data testing? Sabina, yes. If you combine Rhino with Grasshopper and there are some plugins, there are some advanced plugins. So you can pretty much do all that in Rhino and Grasshopper. Okay. Not many questions on YouTube though. How are you guys on YouTube doing? Let's have a word here. Are you with me? Okay. Shy bunch of audience today. All right. So let's talk about Rhino. So Rhino, when you open it for the first time, it looks a bit intimidating, and I know that. And all of the students that I have come across with who have tried to explore Rhino on their own, uh, you know, are usually taken aback by it slightly before they feel comfortable with it. So let's talk about Rhino and Grasshopper. So Rhino, there's a question: what about Revit? Can we do parametric architecture with Revit? Yes, we can do parametric architecture with Revit. There's a plugin called Dynamo that has similar capabilities like Grasshopper, but Grasshopper existed from the later 90s, and it has a very huge community. So just it has a lot of plugins, it has a lot of support and help available on the internet. And right now, as we speak of it, maybe Dynamo would pick up the pace, but Grasshopper is much more powerful than Dynamo. And you can also integrate Grasshopper with Revit, or you can integrate Grasshopper with ArchiCAD. ArchiCAD is also a similar tool like Revit. Okay, where do engineers intervene in the parametric design process? So, Mihala, engineers, when architects are designing buildings parametrically. You have, if you are an engineer, you need to understand how parametricism works, because you will have to simulate a lot of those things. And based on generative designs, uh, okay, let me explain you about generative designs as well. So the best part of computation is you can use artificial intelligence in here. In Rhino and Grasshopper itself, you can use artificial intelligence and machine learning to tell the computer. So if I'm here and if I have to design a bridge, and if the bridge goes like this, and these are some support members on the bridge, so what I can do is I can ask the computer to evolve this design and try out different shapes, and based on the feedback it gets from the design and apply loads on it, and computer would do all of this stuff automatically. So it would try out different shapes, right? And it would try out some crazy shapes as well, and give you an output of what is the most optimized, what structures are performing the most. So maybe if I would like you to go and research about Morpheus. There's a building called Morpheus, designed by Zaha Hadid architects. So the structural members are actually on the exoskeleton. So engineers step in there when it comes to parametrically designing something. How does computation design and parametric design are connected? Are not the same, right? Yes, Irene. Computation design and parametric design are different. Computational design is a broader umbrella in which parametric design comes in. Computational design is where you design anything using computational logics, and it does not necessarily mean that you have to design buildings or graphics. It could be pretty much anything. It could be a code that you have written, and it is doing something computationally. So that is what computational design is. Whereas parametric design is, your design is being regulated through some parameters like sun, wind, and many others. So that is what parametric design is. What about Houdini? Is it now popular in the architecture field because it has a great capabilities in algorithmic design? Yes, Ibrahim, Houdini is gaining popularity among the game designers, but for architecture, Grasshopper is much more preferred. But definitely, Houdini has a lot of potential, and you can pretty much explore that. How the application of parametric design to construction works process, what are the first steps? Okay, Sabina, I'll circle back to this question towards the end of the end of this particular session, because we'll be covering things about construction as well towards the end. Okay. uh, all right, so let's talk about Rhino. So when if you guys are looking at it for the first time, it looks intimidating, right? But don't worry. You see curve is written over here up on the top, and there are some tools in here, and similar tools are here. It says curve tool here, and similar curve tools are here. And if I'm back to standard, some of the curve tools are also here. So it is just that Rhino has same tools placed at multiple locations. So that's why when you hover through it, you think that, oh, there are so many tools. How am I going to learn all of this? And it is so complex. How am I going to make sense out of it? But it is fairly easy once you start off. So these are four viewports in which we visualize our geometry, and you can double click on any of the names to maximize it. So top, perspective view, right view, front view, right, plans, elevations. And down here are the snap settings, just like AutoCAD, right? So I'll maximize the perspective viewport. And let me also bring up the whiteboard and let me explain a couple of basic concepts before we begin. So very quickly, let me explain, if some of you are also new to 3D modeling and stuff, so you'll get a idea about it. So uh, for computers, this is something that you might have, if you are from architectural background, you might have studied in like first, second year of your architectural education. So this is a point. Okay, I'll write a point here. So if I talk about a point, point is basically dimensionless. And Point is dimensionless. What that means is it has coordinates, three coordinates, x, y, and z coordinate, right? And if you join two points together, making a line, line has one dimension and it has a length, right? It has certain length. And if you actually combine multiple lines together, you get a shape, and it is 2D in nature. It has length and it also has breadth. And if you combine multiple 2D shapes, so I'm just stepping right back into Rhino. Let me just quickly give you an idea here. So let's call it form. So it is 3D in nature. So shape would have area with it, form would have volume. And what that means is it basically has certain height, right? Now you can break down this 3D form into 2D shapes. So you see, this is one 2D shape, this is another 2D shape. So you can always break down a higher dimension object into a lower dimension object. Okay, let's come back to Rhino and let's do some interesting stuff here. As a beginner, is it better to learn Rhino or Grasshopper first? So Mola, Rhino and Grasshopper go hand in hand. So you need to have a very basic understanding of Rhino in order to make most out of Grasshopper. Okay, and you'll see how. We'll cover that bit here today. All right. So it is the UI of Rhino is just like AutoCAD. So you can just type in point, hit enter or space bar, and wherever you click, you'll make a point. So you see, I made a point, and these arrows are basically through which I can move this point in the 3D space in X, Y, and Z axis, right? And I can also make points from here. So I can make points from here. All right. And then I can make lines from here. Let me give you this very basic idea of it, and then we'll make some cool parametric stuff today. And so these are basically polylines, and then there are curves. Let's talk about curves. Curves are like very interesting, and you can in Rhino and Grasshopper you can make organic stuff very quickly, very effortlessly. So in order to make a curve, there are two types of curve in Rhino. The first one is interpolate curve or interp CRV. The command is interp CRV. You can also activate it by using the second option here in the menu. So if I use interpolate curve, and when I draw like this, you can see that I'm making a curve that is passing through whatever point I'm clicking. So whatever point I'm clicking, the curve is always passing through them, right? And there is a second type of curve that is called NURBS curve, or you can simply type in curve to bring that one. And it is kind of like SPL in AutoCAD. So if I make it, you see that now the curve is not passing through the points that I'm making, rather the shape of the curve is being approximated through those points. So I'm basically drawing the control points of the curve. I hope that makes sense to you. So these are two different types of curves. Now in Rhino, you could make some basic geometries. These are some basic geometries that you could make. So this is like cuboid, and you can change the view style from here if you if you click on this arrow and if you select shaded or rendered. So you can change the view style. So this is a cuboid, and let me make a sphere on top of it. So this is a sphere, and these are two different objects, right? What if I wanted to combine them in one? So I'm just covering this very basic tool so that you can, right after this session, you can get started with with creating some of these basic geometries. And towards the end, we'll also cover some advanced geometries as well of creating some organically advanced geometries. So these are two different objects. Now what I can do is I can come here in Boolean union and I can choose Boolean union. What it would do is, if I click on Boolean union and select both of them, hit spacebar, it made it one single object. It combined them together. I can press Control Z to go back in time. I can press Control Z to undo. And the next one is Boolean difference. So if I choose Boolean difference, if I select this, hit enter. If I select this, hit enter. So it would just subtract that sphere from this cuboid. And there are a couple of iterations of the same tool. So I would encourage you guys to try this out in your free time. So this is how you make basic geometries in here. Let's try something organic, shall we? Are you guys? Do you guys want me to try out something organic that looks interesting, that has certain flow to it, and so that we can quickly get started with organic modeling? Okay, great. So before that, let me go to the whiteboard and explain you how computer understands surfaces. So the surfaces or all those geometries, let me go back to Rhino. So all these geometries that you see, how does computer understand it? So think of surfaces and think of these like a cotton fabric. Okay, forgive me for my drawing here. So cotton fabric looks something like this, right? It has threads that are interwoven in both the axes that approximate the shape, that make up the surface. So similar is the case in softwares, especially in Rhino. So the horizontal ones are called U and the vertical ones are called V. Okay. So there are these threads. So imagine a cotton t-shirt that you wear. When you wear it, it takes your shape. If you throw it on the couch, it would take couch's shape. So that is how computer makes surfaces. Now what I want to accomplish here is, in the first exercise, what I want to do is, I want to have a curve, first curve, and a second curve. Okay, so these are two curves. And I want to make a surface between these two curves that approximates the shape of these curves, right? So how would I do that? And how would the computer interpret it? So there is a command through which you do that, but I want you guys to understand the concept behind it. Because if you understand the concept, you can learn new tools very quickly, and you can come up with your designs very quickly. So instead of just learning the command, let's see what exactly computer does. So computer, in order to make a surface between these two curves, what it would do is it would break down this curve into some number of points. So I'll make 5 for example here, 1 2 3 4 5, and 5 here. It Computer would do it infinite number of times, or uh, very many number of times. So if after it has divided it, it would number it up. So the counting in computer starts from 0. This is very crucial thing. Counting in computer starts from 0. So it would say 0 1 2 3 and 4. And similarly here as well, 0 1 2 3 and 4. And then it would connect 0 with 0, 1 with 1, 2 with 2, 3 with 3, and 4 with 4. Now it has gotten V lines. Can you see these are V lines, the vertical ones? And then what it would do is it would again break down these red lines into some number of points. So let's say it divides it into 4 points again. So this would be 0, this would be 1, this would be 2, this would be 3. This would be the new numbering system. And again 0, 1, 2, and 3, 3, 2, 1, 0. And I'll speed it up, right? And then it would finally connect all the zeros in here as well, and it would connect all the ones and the twos and finally the thirds. And there, that's how it will make up a surface. Okay, so let's try that out. Let's try to do this in Rhino. So what I'll do is I'll select all of this stuff that I have just made, move it aside, move this guy aside as well. And if I select it and if I click on this light bulb icon, I'll hide it. I'll hide the preview. So let me also move this aside and also hide the preview. Let's start off by making two fresh curves. So let's say this is the first curve, and you can spend your sweet amount of time in making these curves. I'm just doing something quickly here for the example. So there are these two curves, and if I go to the perspective view again, let me move one of these curves to some height, and I want to make a surface between them. So in order to do that, there is a command called loft. If I type in loft and hit enter and select both of these curves, hit enter again. So it tries to make a surface between them, but there is some sort of error if you have a look. So the error is basically I drew one curve from this direction. So this was 0 and this was, let's say, the fifth point when it divided everything. And I drew the other curve from this direction. So this was 0 here and this was 5. So when it started stitching it together, it connected 0 with 0, 5 with 5, and so on and so forth. That's why it gave me a weird intersection. So let's fix that intersection. I'll just select it and delete this, and I'll rotate this curve. Okay, let's try that out again. So if I type in loft, hit enter, select this curve and this curve. Okay, well, that's weird. So there is a command called flip curve that flips the direction of the curve. Okay, let's see if that did it. Nope. All right. Maybe I'll have to draw another curve altogether. But let's see. Yep. So the curves were on different in different directions, so that's why it was kind of intersecting them. So I kind of made this surface out of two curves, and you can see pretty much I'm trying to give you a preview of the way it would divide and connect all the curves together, just like how we tried here, right? So you can see the V lines. So I'll say do not simplify and I'll hit OK. So I have this geometry here with me. Now the problem is, okay, before discussing about the problem, let me move this surface aside. What if instead of two curves, we had three curves? So let me make another one here. Okay. And let's run the loft command again. If I hit loft, select all the three curves. And the order in which you are connecting or selecting the curves is very important or crucial as well. So if I do this, hit OK, this is how it looks. This is how the geometry looks right now. And you see, if I be a little more precise with it, I can design various different curvilinear forms with it. But the only problem is, if I come back here, if I select this curve, and if I make any change to this curve, my surface does not update with it. The surface does not update with it. You would have to kind of delete this surface and do the loft command all over again and run it again to come up with the new geometry. But we understood that through parametric architecture, through computation, we can fix all of that. So let's bring in Grasshopper at this moment and let's explore some of the things in Grasshopper. So what I'll do is I'll set this aside, I'll set these curves aside and probably also hide them. So in order to launch Grasshopper, now this is where the fun begins. In order to launch Grasshopper, just type in Grasshopper and hit enter, or you can click on this green bug icon as well. And for Rhino 6 and Rhino 7, Grasshopper comes pre-installed, so you do not have to install it separately. You can pretty if you have installed Rhino and Grasshopper, you're good to go. Okay. Okay, so let me go to file and I'll hit new document and let me maximize it. So let me give you guys a quick uh, refresher of a quick introduction to Grasshopper. So up here are the components that we use as I showed you earlier in the presentation, and down here is the canvas through which we connect geometries and we explore certain stuff. So let's what we do is we drag components up from the top here and place them here in the canvas. Orange color means that the component is empty. Orange means that the component is empty. And when you just drag it up from the top, it would usually be empty. Okay. And red means that there is some error. White means that it is working fine. This this here is input. Okay. And this here is the okay, the pen wouldn't work here. This is the output. Okay. And you connect the input of the output of one component to the input of the other component. All right. And right in the center here, here is where the processing takes place, where the piece of code is written and where it processes the geometry. All right. Now let's dive back into the practical stuff itself and learn something while creating some geometries. Okay. Okay. So okay, one more thing that you guys have to understand. Grasshopper is very tightly integrated with Rhino. So whatever you do in Grasshopper, it will not show you a preview in Grasshopper. It will show you the preview of the geometry, whatever transformations or whatever things you do in Grasshopper, the preview of that would be shown in Rhino. So whatever you do here in this window here, everything would show up on this Rhino screen. So the best way to work, if you have a dual monitor setup, you place both of them in a different screen. Or if you have a single monitor, you can just place it on one half of your screen like this. And let's start by making a couple of points and bringing them to Grasshopper. So I'm making a couple of points in Rhino. Okay. So I made like 4 points in Rhino. And if I double click in Grasshopper, I can type in point. And this icon in black, this usually is used to reference something or to bring some geometry from Rhino to Grasshopper. So what I want to do is I want to tell Grasshopper that this point that I'm trying to use, this would be the point here where my cursor is right now. Okay. So this is what I want to convey to Grasshopper. So in order to do that, you right click on the component, you right click on the component and you say set one point. You click on set one point and select any one point. And now you see that when I'm clicking on this point, this particular point on Rhino screen is also getting a green preview. All right. Can you see that it is kind of getting a green preview? People on YouTube, is the stream quality okay? If someone can give me a heads up on the chat box on YouTube. Okay, meanwhile I get a response. Let's move further and see what things can be explored. So once you have once you have set up these points, and now the best part is when you move this point in Rhino, the point of Grasshopper automatically updates as well. So if I give you an example, I can type in deconstruct point. What this basically does is this disintegrates whatever input comes in here into XYZ component. So what does a point have? XYZ coordinate. So if I connect this point in here, and then there is something called panel. Panel is for us. We, if you want to see what is the output coming from any component, you connect it to a panel. So if I connect X to a panel, and if I connect this Y to a panel, and if I connect this Z to a panel as well, you can see that the coordinate of this particular point here, the one that is highlighted in green on Rhino, the coordinates are -32, -158, and 0. And have a look, when I change the position, the coordinates update automatically. So you don't have to do anything with it. So let's try to make a line. Let's start off by making a line, and gradually we'll make something very interesting out of it. Probably in the next 15-20 minutes, we're going to make something very interesting out of it. Okay. So let me also bring up this point in Grasshopper. So I'll just double click here and type in point, right click, set one point, and I'll select this one. And then there is a component called line. So this component that you see here, if you hover over it, it would also give you a pop-up message. Create a line between 2 points. That is exactly what we want to do. So the start point would be this one. I'll connect this in start point. And the end point would be this, the second point that we referenced. And if I'll connect it to the end point. And you see it made a line. And now when I'm changing the position of this point, everything is automatically updating. And you see that? The line is automatically changing its location. Okay. If I check the output from this line, if I use a panel to check the output, it says line and the length is 169 units. Okay, so that was about line, but it is kind of boring to bring one point at a time in Grasshopper, right? If there are 100 points and if you have to bring all of them one by one, that would be quite a task. So we can also automate that, or we can also, do something about that. So if I double click and type in point, if I right click and if I go to set multiple points, now I can select multiple points at once. So I'll select this one, I'll select this one, and I'll select this one, and I'll hit space bar. And now when I'm selecting this particular point, you see that all the 3 points are getting highlighted because this particular component is storing all the location of all these 3 points that I just selected. Okay. So what we can do out here is, let's make a curve between the points that we have just made. So in order to make a curve, what we can do is I can type in, let me bring it here so that there is a bit lesser confusion. So just double click and type in curve. Oh, sorry, interpolate, because I want to make an interpolating curve. And you can, right now this component is orange, that means it is empty because we did not give it any vertex or we did not give it any point, right? So if I connect this point and vertices here, look what happens. It turns red. Red means that there is some error with the component. What is the error? In order to get the error, just click on this balloon and it says insufficient interpolation points for a curve, because right now we are only giving it this one point here. Right now, we are only giving it one point. You can turn off the preview of everything else that you don't want to see by selecting all of them, middle clicking and clicking this, releasing the middle click on this blindfolded guy. So I gave it this green point, and a curve cannot be made between one single point. So in order to connect this one, I'll press and hold shift. So I'll also connect these 3 points in here by pressing and holding shift. And there I made a curve. And the best part about this curve is if I change the location of any point, the curve would automatically update. Let's try out a different type of curve, and that's called NURBS curve. So I'll give it the same set of points again, but this time I have a different curve. Can someone tell me why do I have a different curve? Although the points are same, exactly the same, why are there two different curves? Um, Anyone in the chat box, why are there two different type of curves when the points that I gave it are exactly the same? Anyone. I just explained it while I was explaining Rhino. Meanwhile, anyone who has joined us new, leave your email ID and your full name in the chat box so that we can share the resources and these files that we are working on right now with you through email. And if you want to join the WhatsApp group on which we keep on posting educational stuff and things related to parametric architecture, you can do so by joining by clicking on the link that is shared in the chat box. All right. Okay. So, okay, I have an answer in the chat box. Because the interpolation point, and yep. So the difference is, for the first time, I used interpolate curve. What interpolate does is it makes sure that the curve always passes through the points. Okay. The second one is a NURBS curve. What NURBS curve does is it makes sure that the curve is being controlled by those points and is not passing through those points. So that is the difference between both of them, NURBS curve and interpolating curve. Okay. So now if I double click and I want to make a surface between them, so I can double click and type in loft, the command that we learned in Rhino. So if I type in loft, what would loft do? It would try to make a surface between this curve and this curve, right? So let's give it both of these curves. I'll give it this one and I'll press and hold shift and connect this one. And as soon as I do that, you can see that it made a surface here in Rhino, right? Also, the things that I made in Grasshopper, I cannot select them in Rhino. So I made this surface in Grasshopper. If I want to select and do something to it on Rhino, I can't do that because it is being controlled through Grasshopper. But the best part is now if I move these points, have a look. The curves update and the surface that we made also updates simultaneously. So isn't that cool? Everything is kind of automated and adopts to whatever we want it to do. So if I check the output from this loft, it says untrimmed surface. So we got a surface out from here. Okay. If there is any question, keep posting that in the chat box. And um, now is like the finale of this session. Let's do a finale exercise then. All right. I'll move these points aside. I'll hide them. By the way, you can right click on this to show all the hidden objects. I'll select it and hide it. Okay. So let's make something that resembles parametric, that looks very alien, that looks organic and looks something looks interesting, right? So I'll go to the top view and let's start off by making a couple of curves. So let's say this is one of the curves and okay, let me make another one. Let's say this is the other curve and let me make another one. So I'll just select this one again and I'll probably make a smaller one this time with some tight curvatures throughout the edges. So let's say there are these three curves and let's move them on the z-axis so that they are placed at a, at some distance from one another. Okay. So these are three curves. And now I want to do things on it parametrically using Grasshopper. So if I come back to Grasshopper and if I double click, I can type in curve and use this black icon of curve to bring to reference curves from Rhino. How I would do that is by right clicking and I'll say set one curve and I'll select one of the curves. I can press Ctrl C and Ctrl V to make a copy of the component. Again, I can right click, set one curve, select the middle one, do the same thing all over again and select the top one. I could have also right click and I could have also done set multiple curves and selected all of them at once. But for the sake of this example, to make it easy, I mean to explain on a pace where everyone is on the same page, uh, I did it 3 times. Okay. Can we control the points through Grasshopper? Uh, no, we cannot control the points through Grasshopper. If the points were made in Rhino, they will be controlled from Rhino itself. Okay. So let's make a surface between these curves. So I'll just type in loft and I'll connect this, press and hold shift, connect this, and press and hold shift and connect this one. And just like that, made a very organic sort of fluidic looking surface here. And the best part is, if I change the shape of any of the curves now, have a look. The surface automatically updates. So if I change the shape of the curve, the surface automatically updates. I don't have to run the entire commands, the line of commands all over again. So while you're designing something, this comes very handy that you want to try out 10 different things, but you don't want to repeat all the process all over again. So if you're using Grasshopper, pretty much everything stays put, and you can experiment with your design, and everything would automatically be replicated uh, on whatever iterations of the designs you're trying. Excuse me. Yep. So now let's do something interesting over it. I'll hide these curves and I'll double click and type in surface so that I can store the surface that we created in this loft in here. Okay. And I'll turn this off. Grayed out means you have turned the preview of that particular component off. So something is grayed out, that means you have turned the preview off. So uh, once I have this surface, what I want to do is I basically want to find out the center point of this surface. And I don't know the dimension of the surface. I don't know how it is oriented in the 3D space, what is the curvature and all of that. But still, I want to have some sort of control over it where I can go anywhere on the surface on my wish. So to do that, there is something called evaluate surface. And what evaluate surface does is you give it any one surface and it will calculate the dimensions. It would take care of all those things for you without you being worried about the dimensions and the orientation of the surface in the space or the geometry in the space. So if you connect it like this and you click on reparameterize, and I'll explain what reparameterize means in just a bit. So connect the surface on evaluate surface, right click, reparameterize it, and connect an MD slider with it. And you see, when I connect an MD slider, a point appears on the surface. And when I move this graph, I can pretty much go anywhere on this surface. Can you see that point is moving on the surface? And based on the location of this graph on the right, the point is moving here and there, right? Let's try to understand what exactly is happening. Let's go to the whiteboard. Again, I want you guys to understand the concepts behind it, so Grasshopper would become easier for you, and it wouldn't be 10 different 20 different commands that you are trying to memorize and then trying to think, oh, when to use what and how is it actually working. So now I'll give you a very basic example here, nothing too technical. So imagine this is a piece of rope. Okay, this is a piece of rope, and the length of this rope is, at this point the length is 0, and at this point the length is 100. Okay, so what would be the midpoint? What would be the length at midpoint? 50, right? And somewhere here would be 75, and somewhere here would be 25. So now what reparameterize does is, reparameterize. Now what reparameterize does is, it will keep the original length of the rope. I'm explaining this in 2D and then I'll move to 3D. It will keep the original length of the rope, but it would change these numbers. It would change these numbers. So kind of like shifting the number line. If you must have studied it in grade 6 or in your junior schooling years, it would change the number line. So This 0 will remain 0, but this 100 will become 1. Now, if I have to locate the midpoint, what do I have to do? Irrespective of the length of the rope, I just have to tell it that I want to locate 0 0.5 and it would give me the midpoint, or 0.75 or 0.25, right? So I can go anywhere on the rope by just moving between 0 to 1, irrespective of the length of the rope. So similarly, when you're dealing with 3D, let's say this is a surface, okay? Let's say this is a surface, and if I write coordinate numbers on it, so this would be 0, 0, 0, comma 0. This would be x, comma 0. This would be 0, comma y, and this would be x, comma y, right? Just the basic number system. The length and breadth could be anything. So now if I reparameterize it, now when I reparameterize it, this 0 and 0 remains 0 and 0. X becomes 1, and this y also becomes 1, and this becomes 1 and 1. Now if I have a graph that starts between 0, 0 and goes up to 1 and 1, I can pretty much go anywhere on this surface, right? Are you guys with me? A little thumbs up on the chat box would do, so that I understand that this particular concept went through your heads, and it did not go over your head, right? So do you understand how reparameterize is working here? Okay, great. So let's come back to Rhino and Grasshopper, and let me show you this entire process all over again. So if I just double click and type in evaluate surface, and if I connect this surface in here, right click reparameterize, and I can connect an MD slider here. So MD slider is basically a graph that starts at 0 and goes up till 1 and 1. So if I connect it here, now there's a point, and you see when I'm coming to 0, 0, it comes near origin. And when I go to 1 and 1, it has come here. And when I come somewhere here, it came to the opposite end. So I can pretty much go anywhere on this surface by just using this evaluate surface and MD slider by just reparameterizing it. Now, what I want to do is I want to make a cone at this point. I want to make a cone on this point that we have just made. So what I can do is I'll just type in cone, and in the base I can give this frame here. Frame is basically the plane of this particular point. So if you have a look at the camera here, so this is my pen tab. So if this is the point, plane is telling how is this surface oriented at that particular point. So it would just give us the 90-degree idea. Okay. So if I connect this frame in base here, and in radius, let's connect some number. If you double click and type in any number, a number slider would appear in Grasshopper. So I made a radius of about 8 units, and let's give it some length like 15, or let's increase that. So you can see that I just made a cone, and if I want to reverse the direction, if I want to have it in the other direction, what I can do is I can do minus, and I can subtract 71 from 0, so it would give us minus 71, and connect that in length. So now the cone is in other direction, and the best part is if I change the location of the point, you can pretty much see how this cone is moving, right? Let me change the preview style here. Okay, so I'll select this here, and now have a look how when I'm moving this particular point on this graph, the entire cone is moving. Now, this is not what I wanted to accomplish. Now, what I want to do is I want to divide this entire face into smaller panels and then have cones on each one of them. Do you understand? So this is if this is my original surface, I want to divide it into panels, and I want to have a cone on each one of these. Okay, so that is what I want to accomplish here. So what I'll do here is I'll select all of this, move it aside, and I'll turn off the preview. And let's forget about it for a while. So we have this surface here. So first of all, I would like to divide this into smaller panels. So in order to divide it, there is something called isotrim. Now, what isotrim does is you give it a surface and you give it some locations, and it would divide the surface into panels. So kind of like stitching. So in order to give locations, just stay here with me, and I'll explain what exactly I'm doing in just a bit. So there is something called divide domain square, and if I connect this surface here, and if I give it here, and let's give it a u and v count of, I don't know, 15 by 15. I want to divide it into 15 by 15 grid. Let's turn this off, and let's change the preview style back to the normal. So you see that I have just divided this surface into multiple panels. Can you see as I'm moving the slider, the number of divisions are increasing or decreasing? Now, what exactly did I do here in isotrim and divide domain square? So basically, consider isotrim like a scissor. I'm using this anomaly. So consider isotrim like a scissor and divide domain square like a tailor. So when a tailor has to cut down a fabric, what does he do? If this is the fabric, first of all, he would take a chalk and make some markings on it, right? Of where exactly it has to cut it. So that is what divide domain square does. It makes marking on it on the surface. And isotrim is like a scissor that will just cut this surface on these markings. So if I come back here, have a look. Isotrim is cutting it down, whereas divide domain square is telling it where exactly to cut. Okay. Now, if I actually bring up a panel, this was our initial surface, and if I connect it, it was one single surface. And if I connect panel to isotrim now, you can see that there are a lot of surfaces now. There are 179 plus 1 because counting in computer starts from 0. There are a total of 180 surfaces. Why? Because 20 into 9 is 180. So there are 180 surfaces, and these are individual surfaces that are placed right next to each other. Now, have a look at the magic that happens. So we made a working algorithm in which we found out the middle point of the bigger surface, the entire surface, and we made a cone on that, right? Now, if I use these surfaces, if I give this input in surface here, and let me bring this on, have a look at what happens. It made cones on each of these panels. And let me change the preview style. And let's select this. So it has made cones on each of these panels, and I can control the location of these cones on those individual panels by moving this graph. And I can also control the radius of the cones. I can make it smaller or make it bigger. I can control the extrusion as well. How long are the spikes? And I can also control the number of divisions. I could increase the number of divisions to my liking. And let me reduce the height a little bit. Oh, that seems about right. And I can also go back to Rhino, wherein I'll select everything else and hide it. So these were the initial curves. These were the initial curves through which this surface was made. Have a look what happens when I try to change the surface. So I'm selecting these points, and I'll move these points to change the shape of the curve like this. And as soon as I release the button, have a look. The script automatically adopted to the change shape, and all the cones were replicated. Now, instead of making cones, you could make perforations. You could make I could have made cones of different radiuses and have a parameter to control the radiuses. I could have made different lengths. I could have made perforations, circulars, rectangular, triangular, whatever sort of perforations I want to make on these faces based on some algorithm. And I could have tested out what looks best or what performs best in my context, and I could have experimented with it, and Grasshopper would automatically replicate everything. And these are basically the parameters. All these things that you're seeing are the parameters through which everything is getting controlled, and that is how parametric architecture evolves. So the best part is you never lose editability. If you have made working algorithm for, let's say, one building, you can apply the same algorithm to the other building. Or let's say for one facade of a particular building, you could apply it to some other facade, or you could tweak it and evolve it further. So that is the best part that comes out of parametric architecture. And have a look here. So I'll make another surface here. I'll make a surface like this. I'll type in rebuild and press F10 here, and let's change the shape of this surface. So Rhino has kind of a very intuitive modeling, and once you get comfortable with it, you actually love it. How intuitive it is, and you know how organic modeling is so easy on Rhino. So I have made a surface on Rhino here, and I want the same script or the same algorithm that worked on this surface to work on this one. So what I can do is, this was the surface. So I'll just double click, type in surface. I'll right click on this one. I'll say set one surface, and I'll select it here. Hide it in Rhino and have a look. If I connect this surface here, the same algorithm, and let me change, since I did a minus 28, I'll connect positive 28 here and have a look. The same script with very minor adjustments worked like a charm on this surface. So that is the power that parametricism offers us. If there are any questions, you guys can start posting them in the chat box. What if we want to add multiple cones and in a particular distance? Uh, okay, I did not get that question, Sabina. If you could reframe it. Okay, so let's. Uh, this is how Rhino works. Let's try. I'll kind of minimize it. When I send you the scripts after the session tonight, you'll receive scripts that will have some more components here. So that would basically be for you to explore and to create some geometries. And I would personally love to see your progress as well. So do share it with us on Instagram and on various different social media handles. And if you have already joined the WhatsApp group, you can share it there as well. So now if I minimize it, that brings me to the closing presentation for today. And let's have a look. Meanwhile, if you guys have any questions, keep posting them in the chat box. How to open a hole in the panels and how to adjust the area of opening. So, Tunahan, we can definitely do that. We could loft, you could make a surface, you could make a circular or rectangular opening, whatever the shape of hole you want, desire to, and you can loft that, or you can patch that with the external boundary in order to make a perforation. So, you see, it is slightly complex, but when you explore it, if you understand the concept behind it, you can pretty much attain that, Tunahan. Okay, so the word of parametricism and what is the scope of parametricism and how we can explore it further. Let's have a look. And this one will be, trust me guys, this one will be a very short presentation. Probably I'll take like another 15 minutes, and this would give you this would lend you an idea of how exactly the word is adopting to parametric architecture. So construction, I mean, since most of us are from architectural background, You must have seen works from Zaha Hadid, Bajar Kingil, Santiago Calatrava, Frank Gehry, and multitudes of architects that employ parametric architecture in designing. So by just looking at it, you can see that there are these curves, or this was a rectangular plane that was kind of twisted. And then there are these modules that were 3D printed and assembled on site. So construction industry definitely has a requirement of parametric architecture. Let's see what else what else can benefit from it. So by just a very basic, very brief session from today, you can see that if you make some of these curves, maybe on CAD or on Rhino itself, and bring something like this, some cross sections like this, right, and loft them together, you can pretty much get parametric benches like these. So you see how easy it is. You just have to learn to break it down. You see, parametricism is everywhere in the leaves, in the drought patterns, as I explained in the earlier. It is everywhere. The way the birds fly, the ants move, there is algorithm everywhere. You just have to learn to interpret it or break it down. So for nature, everything that you see around yourself, I see a glass, I see a mug, interior walls, benches, chairs, tables, everything could be designed parametrically. And here is this automobile. So automobiles are also being designed parametrically now. And you see that there is something called attractor point that were used to kind of control these black openings in the tail light. So everything that is closer to this point has smaller area of black, and everything further away from it has a greater area of black. And a similar thing is happening here, and a similar thing is happening here. So, or you see the entire vehicle is not designed parametrically, but you can design small modules, small details parametrically and start employing them. And fashion industry, I mean, if you just search for parametric clothings, you'll come across things, and there are designers. I'll probably share some resources on the group where you can read about it further, how these clothes are made. Um, this is basically program deformations, where these deformations are planned beforehand. Fabric is stretched out and then 3D printed. There is deformations are 3D printed, and when the cloth or fabric is released from tension, it takes shapes like these. And this footwear is like the most interesting example that I like to give. So have a look here. So companies like Nike, Adidas, Reebok, they have been doing this for quite a long time now. So if this is a footwear here, and imagine when you stand, just try to recall when you stand, the maximum amount of pressure is exerted in this area and in this area, right? When you stand, the maximum amount of pressure is exerted in this area. So what they did is they wanted to make lightweight footwear. So they started 3D printing it. But now to 3D print the entire shoe sole with the same thickness, with the same material, with the same density of these wires, with the same density, it would increase the weight as well as it would increase the costing of the production of the shoe, the cost of the production. So what they did is, instead of printing with it with the same material, they started realizing that when the pressure is exerted the most here, why not use some hard material here or higher compressive strength material here, and in the other areas we can make the meshes a bit less dense, and it could approximate the entire weight. So as you can see, some of the meshes are relaxed and some of them are very tightly packed. So that is how they bought in this revolution. So the lighter the footwear is, the costlier it is. And now you understand the logics behind it. And jewelry, there's a plugin called pufferfish for for grasshopper, that you can use to design jewelries like these. And let's also see some of the digital fabricational techniques. And this might seem like uh, quite beginner stuff to you, but have a look of the sort of things that we can create. I'll probably be showing that in the next couple of slides. So this is a CNC laser cutter that moves in X and Y direction, and you take your drawings from the computer and directly bring it to the machine, and it would cut whatever material beneath the laser is, right? So CNC laser cutting, and then there is CNC milling that moves in X and Y direction and also moves in the Z direction. So it can make these perforations, make these patterns on whatever the material is beneath it. And then there is 3D printing. I'm sure you must have explored 3D printing, wherein the nozzle moves. There are multiple type of 3D printers out there. Now let's see how we can use things, something as basic as a CNC laser cutter, and design and construct something that is parametric in nature. Enter waffle structures. So this is a waffle structure, the Metropolis Museum. So I'm sure most of you must have seen these images earlier. Most of you must have seen this particular structure earlier. And before I talk about this structure, have a look at, okay, let me bring up, yeah. So this is our Instagram handle. You can, we keep on posting educational stuff here and also updates about the events that we are going to have. So if you're interested, you can check this out. So this is a workshop that we did that I'm trying to find out here. Okay. So this is a workshop that we did, a physical workshop in which students created something like this. And this is the Rhino render. This is something produced from Rhino. And this is the physical model. So all these flaps that you see here were 3D printed, were CNC cutted on an MDF board. And it is a waffle structure. It fit in with each other. And I'm not sure. Can you see these markings in here? Let me see if some other image has a better marking on it. Well, no. So it has these numbers written onto it. So these drawings were directly exported from Grasshopper with these numbers written on it that were directly sent to the fabricator to cut on a CNC machine. And then these were assembled based on the numbers that were written. As simple as that. And this is how it looks. So based on a similar concept is this museum design. So in here, this was realized this is actually a minimal surface. This is a minimal surface, and it has been divided on X and Y axis. And they have these holes in it for the reinforcement bars to pass through, and there are hinges to support the structure. And all of these holes were drilled, designed, and drilled right in Grasshopper itself, and then the drawings were exported. So it is as easy as that. And the thing that you see on the right, this is designed by the Very Many. And if you have never checked the works of the Very Many, I would encourage you to explore it. So these are unrolled geometries. So what it does is, this is again a minimal surface, but it is a very complex looking minimal surface, right? And this is an art installation, and the thickness of this material is less than 0.1 mm, less than the thickness of your debit card. And it is a very sane structure. So now how do they design this? And if I go to Google, maybe somewhere here, and if I search for the Very Many, hmm, let me see. Okay, things like these, or things like these, geometries like these. So how were they designed? And these all were CNC cut. So to bring you to your attention, these all were CNC cut. And how? Have a look here. So if I want to break it down, can I say that this is one strip? Now let me get a piece of paper. Okay. So have a look at the camera. So this is a perfectly 2D piece of paper that I can cut from CNC, right? And if I roll it up, looks something like this, made a 3D structure that is kind of a tube. So um, if I break it down, you can see that there are these strips, and when it is rolled out, it looks something like this. and then there are some holes here, and this end would fold and get attached to this end here through a rivet, and these flaps, these tongues would get attached to the adjacent strips, and thus revealing the entire structure. So the fabrication and installation of this took about 3 days and two people. That's it. So that is what the scope is, and you have to understand that as architects you can't expect the people who are actually building it to be as well versed as you are in terms of parametric architecture or computation design, but you have to find out a way through which you can simplify the whole process. Now if there is someone who's illiterate, who does not know anything about construction, is still, if you tell him that okay, attach this end with this end and keep on attach doing the same, would not require any technical knowledge, right? So it's your job to simplify the construction process as well. Okay. And then we at Equim we have done multiple projects, multitude of projects in which we have incorporated parametricism with modern materials. But then uh, quite some time ago we got an opportunity in which we had to explore uh, parametricism. We had to design a resort in which some open gazebos were to be designed, and the only instruction from the client was that we could not use concrete structure or space frame because it was an agricultural land, and any permanent structure was prohibited there. So we tried to we explored multiple materials, and then we resorted to bamboo, and we combined vernacular architecture with parametric architecture, and this these are some of the designs that we produce. It is still under construction. The construction sadly halted due to COVID. It is still under construction, but some of it is up and there. Let me see why my pen tab is not responding. Okay, it's here. All right. So this is one of the gazebos that is made out of bamboo, and this is a render that it was entirely designed on Rhino and Grasshopper, in which loads were tested, wind loads were tested. The region in which it is built is famous for cyclonic winds. So we tested out cyclonic winds, we tested out sun radiation, how much would it get heated up because it's a hot and humid climate here. So we tested out how much would it get heated, and whether how what would be the effect of wind, how would the load be transferred. So you would be astonished to know that without a single support in the center, you can see that there is no support in the center. The height of the structure is about 20 feet, and the people that we had to work with were were people who made bamboo structures but not complex as these. So we had to give them drawings that from which they could make sense. So what we did is we exported drawings from Grasshopper itself that had all these dimensions and where exactly the bamboo would be bent. We sent the bamboos to the fabricators. It was bent on through machines and pulleys, and then it was brought to the site and assembled by three bamboo workers, and you can see it realizing in real life. It was a nature retreat farm, so it had to had that farm kind of look. And similarly, these structures have been realized wherein this entire thing is sitting between a canopy of pine trees, and this structure is sitting in between the canopy of bamboo trees, and everything was designed in a way that it kind of integrates the computational tools and the abilities that we have, that we can test out the structures beforehand. And that brings me to the last couple of slides. That would be, what is the future of computation in architecture? So right now we are already lagging behind, right? But how do some of the giants, let's say like giants like Zaha Hadid architects, how do they see future of computation in architecture? So they no more consider parameter buildings to be non-living things, and they want it to be alive. And let's see how. So this is a presentation. This is a video that I borrowed from Patrick Schumacher's presentation. So have a look at it. So here it was more of a common seating space in which seats are getting morphed. Have a look. This is a common seating space, general gathering, as time passes throughout the day, some of the benches became tables. Some of the benches actually became conference room walls or partition walls. And as the users are interacting, this furniture is actually changing its shape based on computers fitted into them. And you see, it is not a reality just yet, but researches are live. And 5, 10 years down the line, this is how the future looks like. And this would be true. We all know Zaha Hadid architects, how they have been taking innovations to new heights, and I'm sure this we would see something like this very soon. And let me show you this one. Okay, so now consider that if you have to design, think about it. If you have to design a floor plate that would accommodate, let's say, 1,000 people, an office space in which there would be 1,000 people in there, can you think from a perspective of 1,000 different users as an architect? No, right? You can't think from the perspective of 1,000 different users. But what you can do is you can use AI to simulate 1,000 human beings in there and see how they correspond to that space. And if they correspond very nicely, that means your design is very nice. If they don't, then that means you have to change certain things in your designs. So that is how you will know that not only your design is sustainable, responsive to the environment, but also the best possible design for the users as well. So have a look at this short little video. So this is a human being. He's sitting in the office space. He has to go to the conference room. So you can see what all people he's interacting with. How much does he want to work? How much does he want to engage in conversation? How hungry he is? How much he wants to use the restroom? And what path he chose to come to the conference room. And this in this video here, this is basically a common working space, and the yellow ones are the points where the collision of the people is intermediate. Green is okay collision, and this is like the most interesting bit. So here is a person who's walking down to the reception, and he wants to go to working area or maybe semi-leisure area. So he's stepping towards the working area. So this is how normally a person would enter a building. Now this is an orthogonal view, uh, in which you can see all the floor plates and all the spaces in which people would be reacting. And this is 9 a.m. to 10 a.m. is working when people came to their seats. 10 a.m. to 11:30 is report time, where employees would go to their managers and report, right? And then I'll just move it forward a bit. Yeah, and how they would interact with each other, how different teams would interact with each other in when it's recess or when it's break time, and what sort of routes they would choose. So having informations like these gives you an extra level of control over your design, and you feel confident whether whatever you have designed will be used the way it has been designed or not. So that is the biggest thing that you have to look forward to as well, right? And that brings us to parametrized. So architecture has not been evolved from ground up. I mean, it has architecture always had inspirations. And if I talk about Antoni Gaudi, how did Antoni Gaudi, who is considered like the forefather of parametric architecture, how he evolved himself? If I go to images and if I search for spring experiment, I'm not sure how many of you have heard about his designing methodology. Uh, yes, we can do that in gaming engines, Ibrahim, but Rhino and Grasshopper are, a bit more focused towards architecture, so the results that you obtain out of it would directly benefit um, you. So, string experiment. So, what Antoni Gaudi, how he designed his structures was he used a string, he took a string and suspended some weight on it. So the spring buckled and it looked something like this. And the best part of this spring is right now it is under tensile force. But if you invert it, if you make it something like this, Now, the tensile force equals to the compressive force. Now, this is something related to the structures. You don't have to get into technicalities if you don't want to. But basically, what I mean is this is structurally self-optimized. This is structurally self-optimized. This is how he, got inspiration from for the forms. And you see, these are inverted strings, and these little sachets that you see contain loads or weights inside it, and this sort of things he created, and out of this he created buildings like these. From this took inspiration architect Frey Otto, and he started using soap bubbles and strings to make minimal surfaces. Now minimal surface is another level of uh, is another type of structural design in which you distribute the loads on on the entire shell. And he usually used tensile fabric to design his structures. And if I just search for soap bubble experiment, so you see he did experiments like these. So have a look at this image. I want you guys to focus right now on the screen and have a look at this image here. Once you have filled it in, have a look at this image, and then let me bring this one. I should find it somewhere. Okay. Okay. Yeah. Have a look at this model. So can you immediately draw a connection between this, that was a soap bubble, and where did it go? Uh, yeah, here. And this, right? You can immediately draw a connection. And from this, he built this. Now, let's have a look at Beijing Airport. That was designed by Zaha Hadid architects. So have a look at this structure here. Can you immediately draw a connection between this and this? So Zaha Hadid herself and Patrick Schumacher in many interviews said that they were highly inspired from the work of Frei Otto, and it is not bad. Frei Otto himself was inspired from Antoni Gaudi. So this is how you take inspiration from the masters of the past and create something that is new, that carries the same emotion in the real world, in the present world. Now in this one, the materials are different, the designing techniques were different, the architect was different. Here they either use concrete or they use space frame, but the emotion behind it is still the same. And instead of using soap bubbles, Zaha Hadid architects use computational designing tools like Rhino and Grasshopper. So that is what we have to learn, how we can start taking inspirations from the things that already exist, masterpieces that already exist, and take them to the next level, evolve them to the next level. You don't want to design the car from the scratch that was designed 200 years ago. Rather, you would use the available resources right now of a modern day car to design something new. So do the same thing for architecture as well, right? And that brings me to parametrized. So those of you who are interested in learning about parametric architecture and computational form finding to come up with forms like these, and forms like these, and forms like these, should check this out. Visit equimdesigns.com. So someone from the team will also post the link in the chat box. So let me tell you what this is about. So this is a very new thing that we are this is, I mean, not new as in, we have been doing this workshop for quite a while now, and this is a new concept of teaching students, teaching the people who want to learn something new out here. So this is basically a workshop that goes for 5 days on weekends, and usually the timings are 11 a.m. to 5 p.m. throughout the day. And it starts off with the very basic understanding of Rhino and Grasshopper. So you do not need any understanding of Rhino and Grasshopper. We'll begin from the very basics, very zero level itself, and go on to a very advanced intermediate level in which we try out advanced plugins like Kangaroo, Weaverbird, and Mesh Plus, and we explore methods of Anthony Gaudi, Frey Otto. We do all these spring experiments computationally. We do soap bubble experiments computationally. So for Frey Otto and Anthony Gaudi, it was a lot of work. He had to, suspend the strings, freeze them, and then invert them, sketch them out to get some inspiration. We don't have to freeze it. We can pretty much go crazy with it since it's inside the computer. And for Frey Otto, the soap bubbles were there for just seconds before they popped. Our soap bubbles would never pop, right? So, and then it also has on the next session is scheduled on 8th, 9th, 10th, 11th April, followed by 18th April. So on the fourth day, so you guys can go definitely go on the website and check out the details. So day one would all be about introduction, attractor points, attractor curves, data management lists. Day two is where the fun begins, where we'll explore things like parametric facades, parametric skyscraper designs. So the entire floor plates, the entire facade, everything would be of a skyscraper would be controlled parametrically, and we'll also explore Rhino rendering from it. And then on day three, we'll explore Anthony Gaudi's methods. We'll explore meshes. We'll simulate loads and pressures to come up with self-optimized forms. And on day four, we'll deal with Frey Otto's finding of minimal surfaces and all that, and take it one step further. And on in the end of day four, so for architects, this is like the biggest opportunity. I mean, this is like one of the very nice opportunities. So on day four, we introduced to you to a design competition. And in this design competition, you get your own team that would be sitting globally. Some of them might be students of architecture, some of them might be advanced architects, and you'd be collaborating with them for that competition. And you would have your own team. There would be number of teams in which you will have to compete, come up with a solution of your own. So, and then you'll compete, and on day five there would be design reviews. There are some cash prizes, there are some honorable mentions, you'd get your work featured, you get certificates and all of that stuff. And these are some of the okay, this is pretty interesting. We are pretty proud to showcase some of our participants' work. So all of them were complete fresher who joined, and these are the geometries that they produced within the 5 days. So I'll just quickly go through them. If you are keen on knowing more, you can definitely reach out to the chat support on the website here, and or visit the website. There, the information is pretty loud and clear there as well, and you can explore it. So geometries like these and these. So yeah, you can definitely, and these are some testimonials of how the students felt after they attended the workshop. And this is like very uh, I mean, this is something. Let me copy this video URL and share it on the chat box, and I want you guys to copy the link of the website as well. Have a look at this. This was the virtual exhibition for the last parameterized session that we did, and the exercise was to design an underwater or under ocean set that was entirely parametrically designed. And this graphic that you see here is the work of one of our groups, one of the groups of the participants. So you'll be exposed to creating things like these, and where you'll put together your architectural knowledge that you have along with the knowledge that you'll acquire through the workshop into one single exercise. All right. And the registrations are live right now. The standard registration price, if I talk about in US dollars, standard registration price is somewhere around $135, $140. But right now we are in early bird registration that is ending. I believe almost all the seats are almost gone, so should not be up till 20th. It might end tomorrow or maybe day after tomorrow. So if you enroll through early bird, you can get the same seat for somewhere around $110 or maybe $101. I'm not. You can click here, register now, and it would give you a US dollar pricing. So you can definitely check that out. Okay. And if you're also interested in AI, so this is like beginner to intermediate level workshop. If you are interested in AI urbanized, this is like where we take eco-urban analysis, where we do different sort of analyses. And you can check out about this. These are some of the works from this particular workshop, and you can check out about this. And right now the registrations for this one are closed, but you can definitely post your query and you can get registered. This is an intermediate level workshop. You can get registered as soon as the registrations go live. But parameterize is like a beautiful opportunity that you can definitely explore. Okay, let me come back here to PowerPoint. And okay, so lastly, I would like to explain the importance of documentation. Nothing in 21st century is more important than documentation. If you are unable to express your work to everyone else in a manner that they understand, your work would not gain popularity. So documentation is extremely important both for you and your work, so that you can also track down your progress year by year, month by month, right? So I would encourage all of you to, when you get these files, these scripts today, explore them, take some renders out of it if you know how to use some rendering tools, or take some photographs out of it, screen grabs, and share it with us on social media and tag us at equim_edu or equim designs. Use these hashtags. And now let's open up for Q&A. So if you people who are on Google Meet, if you want to unmute yourself, have a word with me, you guys can now have a word. We can discuss up. People connected through YouTube, if you have any sort of question, you can post that in the chat box right now. And the video would still be up on YouTube. So if you want to revise it, if you want to revisit it, you can definitely go to our YouTube channel and review it. So if there are any questions, um, I would love to take them right now. Okay, so not many questions popping up. All right. So probably I did a great job at explaining everything to you today, and everything is perfectly clear. So that's great. And if you already haven't joined the WhatsApp group, you can join in there, and anything related to parametric architecture, whenever that comes to your head, if you are ever confused, you can post your queries and everything in that particular WhatsApp group that is entirely dedicated to discussions regarding parametric architecture and architecture, digitalization in architecture, basically. So, and I'll be sharing some books and resources on that particular group as well. So you can definitely try that out. And it was really nice having you all. And I had a great session with you. Thank you for showing up. Thank you for joining. And I hope to see you in the future session. Thank you. Bye.